All right. Hello, hello. Welcome again to PyData Global 2024. We're very happy to have you all here. I'm Conrad, again, I'm a co-organizer for the PyData Global Conference. It is my pleasure to introduce Dr. Igor and also Baran, both from WISE, here to talk to us about fast intuitive feature selection via regression on Shapley values. Without further ado, please take it away.
Hi, everyone. Thanks for tuning in. So we will tell you about this new method for feature selection, which we have developed and open sourced. And I am Koseoglu Kraev. I built up the data science team in WISE and have now moved to a principal position. And with me will be Baran, one of my colleagues, data scientist at WISE, who will start the presentation.
Thanks, Igor, for introduction. So today we'll be talking about feature selection. What are the methodologies in the feature selection space? We will then talk about our framework specifically, and then we'll go into more details of the experiments we run with the framework we developed, and we'll talk about more. So let's take a step back and introduce the problem in feature selection. So given an inducer, a data set with features from x1 to xn from a distribution D or the labeled instance space, what we want to achieve in feature selection is that we want to find an optimal feature subset called xopt, which is a subset of features such that the performance of the induced classifier is maximal. Here, the performance of the induced classifier depends on the task that you want to achieve. It could be accuracy, or it could be some other performance metrics. In this space, there are three types of methodologies in feature selection. If you again take a step back and think about the problem once again, and if you try to combine all the features and train one machine learning model on each opt combination, this feature selection problem becomes an NP hard problem with a greater complexity to the end. And so we need efficient methodologies that helps us to basically run feature selection algorithms at scale. And in this space, there are three different methodologies. One is filter methods. They are very basic. They use ranking techniques to rank features and select features. There are wrapper methods. Basically, these are using your machine learning model as a black box and iteratively run feature selection to select optimal features. And there is embedded methods as well, which incorporate feature selection directly into the model training process. Filters, when we talk about filter methods, as I already described, they are very basic filtering methodologies, and they just rank the features according to your selected, let's say, ranker. And in a case of the page you see here, we can select, for example, correlation as our ranker and try to select optimal thresholds. However, one thing to mention here is that relevancy may not mean optimal. So a feature may be relevant to your target variable, but this doesn't mean that it's optimal. So advantages of the filter methods, they are very easy to implement, scales well to large datasets. We also experimented with our datasets at WISE, but there are also some drawbacks with these methods that they lack ability to consider interactions between features, and they are basically prone to give some errors due to noise. If you switch to another methodology called wrapper methods, these methods when compared to filter methods, they are more complex. They are able to consider the feature interactions. They treat your machine learning model as a black box and evaluate the performance of the model on subset of features, sort of iteratively select these features and basically come up with a subset of feature that maximizes your machine learning model performance. Advantages, these performs well in scenarios where feature interactions are important. Obviously, they are easy to implement. Disadvantages is that there is high computational cost because you need to retrain your machine learning model while you are selecting a subset of features, and they tend to overfit on smaller datasets. And on the screen you can see one of such examples where in every iteration you are selecting one feature at a time and train a model, and there are certain steps that your algorithm ends. Another category of feature selection methodologies is embedded methods, and embedded methods, they incorporate feature selection process in the training process, which gives you advantage of considering feature interactions, as these feature selection frameworks, they are already in the training process. They are computationally more efficient because as you train your model, you're also selecting your features, right? So you don't need a separate process to select your features. Disadvantages is that they are dependent on the selected model. So they are not, so if you, for example, run an XGBoost, right, and you have an embedded method, it may not work for another machine learning model. And they can be quite sensitive to the regularization parameters, that hyperparameters that you use for the model, since they incorporate feature selection in the training process. And if we plot all these methodologies on the graph, you can see that embedded methods, they are computationally more efficient than wrapper methods, and they yield a great performance compared to filter methods. Yegor, do you want to take us through our motivation here?
Absolutely. So can we have, yes, exactly the next slide. So first of all, let me briefly introduce to you the Shapley values. And so the Shapley values are a way for any kind of function, in our case, a regression model or classification model, to describe the contribution of each feature. And their wonderfulness is in the fact that they're additive, because generally there's quite a lot of interaction between the features. In any nonlinear model, by definition, the impact of one feature will depend on the values of the others. But Shapley values are a mathematically rigorous way of additively decompose any value of the function into contributions of the distinct features. And in general, this is, again, requires 2 to the nth evaluations of the function, so it's quite expensive. But for tree-based models, such as everybody's favorite gradient boosting models, there is actually a fast algorithm for implementing them, which is available in the Shap package. And so Shapley values, unsurprisingly, have been tried to use for feature selection. The obvious way, of which there is many implementations in both on GitHub and in the literature, is just to use them to see what does the model care about the most. So you train a model, you take a training data set, train the model with your favorite settings, and then look at the Shapley values of the same training set for that trained model, and see which ones have the largest absolute values. And those are the ones that the model cares about the most, and therefore those are the most important ones. And so you use the absolute value of Shapley values across the data set, averaged in some way across the data points, to rank the features' importance according to the model. Now, that is already works quite well. However, it has one problem, which is that it believes the current model is the truth. So it doesn't take into account potential overfitting on the training set. And so that's how we came to our idea. So first of all, to control for overfitting, let's look at the Shapley values on the validation set instead, rather than the training set. And then here is the fun part. The Shapley values must add up to the actual function value and to the value of our model in this case, which means we are now in additive territory, which means we are in classical statistics territory. So we can do a linear regression of the target on the Shapley values. And for example, if our function on the validation set is a perfect description of the target, then all the coefficients will be 1.0 because modal value equals target value and target value and modal value equals the sum of the Shapley values. However, generally, of course, that won't be the case, and the coefficients will be very different from one in some cases. And then we just look, a negative coefficient means this feature is actually pulling the function away from the target. So then we discard that feature. And positive coefficients we can rank by their statistical significance. So now, so this is the beauty of it, that for now we have extended the classical statistical significance apparatus to the space of nonlinear models, in fact, to the space of any model for which you can cheaply compute Shapley values. And so far, I've reasoned for the regression cases, but this also works for classifiers. Classifiers, you have to use the log odds Shapley values, which and then use logistic regression instead of linear, but you still have exactly the same interpretation and exactly the same statistical apparatus with t-values, significance levels, and so on. And then for multi-value classifiers, you don't have just one Shapley value, you have one Shapley value per class or per label. And then we aggregate significances by choosing the largest t-value. And so negative t-values drop out. So with the idea is if a feature is significant for at least one of the labels, it is significant. And finally, we can deal with potential collinearity using regularization, first of all, so collinearity among the Shap values. And secondly, iterative feature dropping. So if the rank of the Shapley values feature matrix is not the rank, if the conditioning number is very high, then we drop the feature with the lowest significance and repeat that, and then refit the linear regression and repeat until the conditioning number gets good enough, and then we can just run the regression on the rest. And this is iterative, but it is a cheap iterative because at each iteration we're just fitting a linear or logistic regression. So in that sense, it is a wrapper method, but unlike all other wrapper methods, you have to fit the original model just once. And for use cases like that in WISE, where we have millions of rows in the data set or tens of millions, and a fit of the model takes hours, this is important. And so here is just a pseudocode, if you wish, or Python is everybody's favorite pseudocode for doing it. So you fit the model once, you compute the Shapley values on the validation set once, and then you compute significance of these features using discarding negative coefficients and using the procedure just described. And while features remain, and one thing is not spelled out here for simplicity, while features remain and the conditioning number is high, you drop the feature with the lowest significance and repeat. And that's it. And so what that gives you is a ranking of the features with respect to their usefulness on the validation set. So this is not one of the methods that actually tells you choose these features. It tells you throw away some of them, those with negative coefficients, and for the rest, it ranks. All right, over to you, Baran.
Thanks, Igor. Let's talk about the experiments we ran while building this framework with Igor. We had an experiment design where we split a data set that we take from Kaggle, that famous Kaggle credit card data set. We split it into training, validation, and testing, and then we selected one model, XGBoost, and we set hyperparameters as you see on the screen. Objective was binary, evaluation was log-loss, boosting routes 100, verbosity, seed, and threads. We didn't pre-process the data, no scaling normalization was applied, and methodologies that we use in our benchmark of our framework with the existing frameworks was Shap-select, our framework, Shap selection, recursive feature elimination, Heisel, and Boruta. And here you can see what each of them does. You can later also search for them and then take a deeper look on how they solve this problem. So in our case, experiment result was like the following. So our framework called Shap-select, it selected 6 features out of the all Kaggle credit card data. The accuracy was very much similar with all the other frameworks. However, since this is a highly skewed data set, we rely on F1 score here, and F1 score of all the frameworks used in the experiments can be seen here, and runtimes, right? It's important that we take a look at the runtime as well. And we can see that only Boruta is the framework that is doing better in F1 score than our framework. But Boruta runtime is significantly higher than our framework. And in that sense, we provide a balance between computational efficiency and performance. And we did more in these experiments. Since we are also relying on the use of p-value, we take a look at what happens if we use different p-value thresholds in our framework. And in our case, for the purpose of this experiment, 5% was just yielding a maximal F1 score. And you can see a distribution of F1 score and the choice of our p-value in our experiments. Igor, do you want to conclude this session?
Absolutely. So as you've seen, we have this method produces a good trade-off between accuracy and performance. And in some settings, likewise, it matters because we have to retrain these models, which ideally would also include hyperparameter tuning and feature selection every couple of weeks because of data drift for some models, for example, fraud detection. And a single run takes several hours. And so, if anything, the table that Baran just showed underestimates the performance difference between Boruta and ours, because the only iterative bit in Shap-select is refitting the linear regression or logistic regression until the conditioning number of the remaining features is good enough. Whereas Boruta refits the original model, which here was not that expensive because the data set is small, but it gets prohibitively expensive as your data set grows larger. So so that's that, and we will of course one data set is not conclusive, so we will be testing. We are already trying to use it internally in WISE, and we will be testing on more data sets, and we'll update the paper once the data is in. But we thought that being open and making it available to the community sooner rather than later is a good thing. So the the package is available on GitHub with an open source license, Apache 2.0, so fully open source, or just directly by pip install.
Thank you very much. I think we can take the questions in Discord channel, right?
Yep, absolutely. I would invite everyone to continue it on Discord. I know there was questions about the links to the slides. Is there a chance? You said you're going to put them in on LinkedIn, and there's the GitHub repo as well. Is that correct?
Yeah. So
Yes.
GitHub repo was on the slides. Yes, absolutely.
Yep. Okay. Cool. If there are any other questions, we do have a few minutes, but if not, we can certainly wrap up. And
I think there's one from Henrik. Yeah, I think as Yogor already mentioned, we are testing out this framework with other datasets. At the moment, actually, I'm running this framework on other datasets that we have at WISE. So that's a yes, and you can also give it a try with your own dataset. And theory, yes. So there's already GitHub link. You can see on the slides, and I think we'll be sharing the slides as well.
There is an interesting question. Why is a feature ignored if the value is negative? So the reasoning is that now you have that we're talking about Shap values, right? So actually, the value of the function is the sum. The value of the function is just a simple sum of the Shap values of all the components. And so now, if you if the function was a perfect prediction of the target, then the coefficients would all be 1. And so now, if the coefficient is negative, this means that the mean square error, if you just leave this feature out, setting its coefficient to 0, and keep all the other features in with their coefficients to 1, you'll actually have a lower mean square error than by including it outright with a coefficient of 1. So literally, what a negative coefficient tells us is just dropping the feature and keeping the rest as is a better approximation of the target than leaving it in. And so we should drop it. But of course, the particular model that we use to Shap values from is not an oracle, so it's a heuristic. It's not mathematical certainty. And you should try it on the model with the hyperparameters they're going to use later, because the results might differ. But it's been a useful heuristic.
Looks like we have a couple more questions if y'all want to.
Wonderful. It's always great when questions are coming. So if Shap-select suggests the number of features is drastically reduced, could this be a signal that we may need to use a less computation intensive algorithm? Potentially, absolutely. However, in practice, in most cases, Shap-select will not reject all that many features. So not that many features will have negative coefficients. So what it gives you then is a ranking of the remainder of the features. So you still might want to do a search of just how the perfect threshold for your case. But that search now is linear, so you just need to move one real valued variable. So you can do, for example, a binary search on the ranked features, rather than having to try out all the 2 to the nth possible combinations of what you should drop. Collinearity features. Could the negative coefficient be explained by collinearity effects? Yes, potentially. Which is why we have this collinearity elimination procedure. So we run a regression, and we take the least significant feature, and we drop it, and we rerun the regression. And this way, if there is collinearity, eventually we'll drop enough features that we expect it to disappear.
Is there any more questions? I think we have just a few more minutes. So if not, oh, yep, here we go.
So the origin, yes. So do we have a feeling of its robustness to the goodness of it for the original model? Well, it's obviously crucial that the original model should be a reasonably good fit. It should be. So if anything, we expect it to be fairly robust to overfitting. But so I would think for the original model, you should overfit rather than underfit. So that potential relationships, so you capture rather too many than too few potential relationships, and then those will get discarded at the wrong ones will get discarded at the regression stage. But this is also why we recommend that you fit the same model with the same hyperparameters, but just on all the variables. Another thing that we've tried, which didn't seem to add much, is that you train a model on all the features, then you throw away some of them, and then you refit your big nonlinear model on the remaining features and repeat. And that didn't seem to add much value. So it really seems that it's enough to just fit the model on all the features and then rank them using that.
Great questions. Appreciate everyone sharing those.
Yes, thanks a lot. And please don't hesitate to reach out to us with your experiences and ideas about this once you've tried it.
Awesome. Well, thank you for presenting today. This has been great. And thanks for everyone for joining us. And as I mentioned earlier, we can continue the conversation on Discord. But for now, let's wrap up. And we are going to start our keynote with Peter Wang in 3 minutes. So we will see you there. Thank you.